In this video, we will use PyTorch to build a working neural network. Specifically, this network will be trained to recognize handwritten numerical digits using the famous MNIST dataset. The code in this lesson will borrow heavily from the PyTorch Learn the Basics tutorial on this page. We do this for several reasons. First, this tutorial does a fairly good job of demonstrating all the code that is needed to have a successful neural network build. Secondly, just like when you import modules in Python, it is a good idea to not have to reinvent the wheel if you don't need to. And finally, when building your own neural networks, it's quite beneficial to start with something that is known working and then make modifications from there to make sure that your own build is more likely to be successful. You will need some necessary background for this video. First, you need some familiarity with Python and Python object-oriented programming. You should also have familiarity with how neural networks work. You can check the Finxter article, The Magic of Neural Networks, History and Concepts, to learn the basic ideas there. You should also have familiarity with how neural networks learn. You can see the Finxter article, How Neural Networks Learn, to learn this subject. You should also have familiarity with tensors. See the Finxter article, Tensors, the Vocabulary of Neural Networks, to learn that subject. Finally, you should have familiarity with matplotlib. Strictly speaking, it's not necessary to have matplotlib experience to follow along on this video, but it is necessary to be familiar with it if you actually want to be able to view image data yourself on your own data sets in the future. And you really will want to be able to do that. So having some experience with matplotlib is very important. Now, you can run PyTorch on your own machine, or you can run it on publicly available computer systems. We will be running this exercise on Google Colab, which provides world-class computing capability, all for free. Plus, they have all the needed libraries already installed and ready to go. If this kind of thing interests you, you can learn more about it going to the Finxter article, Top 4 Jupyter Notebook Alternatives for Machine Learning. So here's an overview of what we will be doing. This article will cover all the necessary steps to build and test a working neural network using the PyTorch library. PyTorch makes building and training and using neural networks easier, and in addition, under the hood, it's written using the very fast C++ language, so the neural networks can provide world-class performance while using the popular Python language as the interface to create those networks. Neural networks and the PyTorch library are rich subjects, so while we will cover all of the necessary steps, we will just scratch the surface of each respective subject. So you will probably, for each of the steps here, there are other things you may want to learn to enhance your skill as a Python neural network engineer. Nevertheless, by the end of this article, you will have built your own working neural network, so you know for sure you'll be able to do it. And you'll simply want to, as I mentioned, you'll want to learn more on each of these steps so that you become more capable and more proficient going forward. Here are the steps that we will be taking. First, we'll have to import the necessary libraries. Then we will acquire the data. Then we will review the data so we have a good understanding of what we're dealing with. Then we'll create something called data loaders, which help loading the data into the neural network. Then we will design and create the neural network. Then we will specify the loss measure and the optimizer algorithm. Then we will specify the training and testing functions. And then finally we will train and test the network using those specified functions. Okay, we are about to import the necessary libraries, but before we do that, we'll want to set up to use a GPU. Again, we're assuming that you're using Colab. If you're using Colab like I am here, you'll want to set up a runtime to use the GPU. And to do that, we go up to the top menu bar and click on Runtime, and go down to Change Runtime Type. And then under Hardware Accelerator, select GPU. I already had that selected, but default is typically none. Anyway, select GPU and then save. Strictly speaking, for this data set, it may not be necessary, but for some data sets it's very clear you get much faster processing using GPU. So it's a good habit to get into setting up GPU for your training. Okay, here are the libraries that we need to import and what they're used for. First, we will import the Torch library, which is basically PyTorch itself, the main PyTorch library, which makes PyTorch available for use. Then from the Torch module, we will import the NN library, neural network library, which is important for building the neural network. Then from the Torch Vision module, we will import the datasets library, which provides the image datasets. Then from the Data Utilities module, we will import the Data Loader library. As mentioned before, data loaders are used to help load data into the network. And then finally from the Torch Vision.Transforms module, we will import the ToTensor library. This is used to convert the image data into tensors so that they are ready to be processed through the network. And here's the code importing the needed modules. We'll go ahead and run that. Next, we need to acquire the data. As mentioned, in this exercise we will be getting the MNIST data as it's available directly from the PyTorch set of libraries. This is the quickest and easiest way of getting the data. If you wanted to get the original data set, it's available at this website. It's a good idea to review this website anyway because it provides some useful information about the data set. For example, one of the things you'll learn is that it's a set of 60,000 images of digits for training and another 10,000 images of digits for testing. But as we mentioned, we will be getting the images, we'll be getting the data from the PyTorch tools for accessing that data. PyTorch provides a whole bunch of data sets available as image data sets and additional data sets. There are also image data sets, text data sets, and audio data sets, and you can click on the links in the article to go to those data sets. So to get data from a PyTorch dataset, we create an instance, a dataset instance from the respective dataset class, and here's the format. So just to clarify, if you go to the images datasets webpage, it lists a whole bunch of different datasets that are available, and those are essentially classes that allow you to create a dataset object from that class. So here's the format: dataset class with some parameters, and then you create you create a an object from that dataset class that that specific dataset class. And that creates the dataset object and downloads the data. And this makes the data then available for working with it. Here is the code for creating our MNIST data sets. So we have excuse me, we have the MNIST data class, so dataset class, so datasets.mnist is the class, and then there are a list of parameters, and we create our object, our instance from that class. So we'll go ahead and do that. And it has downloaded the data and created our dataset object. We want to create two dataset objects. The first one that we did is a training set, and the next one, this is code for creating the test dataset. And we'll go ahead and do that. Here is what these various parameters mean. Root is the directory that the data will be loaded into. So it either creates the directory if it doesn't exist, or if it does exist, it loads it into that directory. Train determines whether the data that's downloaded and created in the object, that determines whether it's a training set or a testing set. Download determines whether you download the data. It will download if it's necessary or not if it isn't necessary. And transform makes transformations to the data. In our case, we're choosing to transform the data to a tensor. There are other transforms that are possible, things like cropping, rotating, things like that. But the only one that we're using in this case is converting the image to a tensor. Note that what parameters are available or even needed vary from dataset to dataset. So you will want to check the dataset web page to see what parameters are listed, and choose what you may need to use. While this method of getting data is convenient and easy, using the PyTorch dataset library, remember that ultimately you'll want to work with your own data, so you will want to learn how to create your own data sets. So that's something else that you'll need to learn that we're not going over in this video. Excuse me. Also, not all data sets contain images with uniform image size. So images may need to be cropped or stretched to fit the fixed number of input neurons. So other transformations, like we mentioned, there are other transformation options. Other transformations can be helpful as well, and that's something else that you'll need to learn, is how to do image transformations. Now that we have downloaded the data and created a data set object, let's review the data so that we know what we're dealing with, so we can understand the data set contents and its structure. So first we'll try the type command on the data set, and as you can see, it's essentially an MNIST object. So we've created a dataset object. It's not a list, but conveniently, it's an object, not a list, but conveniently PyTorch datasets have been designed to be indexed like lists. So let's take advantage of this and use the length function to learn something about our dataset. So length on the MNIST data object is 60,000, and length on the MNIST test data object is 10,000. So our training data set contains 60,000 items, and our test set contains 10,000 items, which is consistent with the number of images specified to be in each respective data set. that's what's indicated on the web pages describing the data set. So let's use type and length functions again to examine the first item in the training data set. So the first item in the training data set is a tuple, and it has 2 elements in it. Now let's use the type function to learn about the first item in that tuple. So that we're looking at the first item in the data set, which is a tuple. We're going to look at the first item in that tuple. So the first item in the tuple is a tensor, and that is likely some image data. Let's examine the shape attribute of the tensor to understand its shape. So we take the first item in the data set, use the and do dot shape to check the shape attribute. And that is a torch tensor of 3 dimensions with 1 element, 28 elements, and 28 elements respectively. And this is consistent with the 28 by 28 pixel structure of the image data, plus 1 additional dimension just containing the entire image data. So let's examine the second item in the tuple. Remember, there are 2 elements in the tuple using a type command, and it's indicated as an integer. And if we evaluate what that is, it's an integer number 5. So that's apparently a label for the image, the first item being an image, and the label being the number 5. So let's use matplotlib to view the images. So we do import matplotlib.pyplot as plt. We'll go ahead and run that. And then plt.imshow on our on our data set item, the image item with gray color mapping. Oops, we've gotten an error here. Let's see what the error is. Invalid shape for image data. So we need to plot 2-dimensional image, but we've got 3 dimensions. So it looks like that extra 1 item dimension containing a whole image is causing us problems. So we can use the squeeze method the squeeze method on the tensor to get rid of any 1 element dimensions, and instead return a 2-dimensional 28 by 28 tensor instead of the 3-dimensional tensor that we actually have. One element dimension and 2 28 element dimensions. Excuse me. So we will try the same command, but with the squeeze method included. And you can see it has now plotted the image. And it's a little sloppy, but it's plausibly a number 5. But that's reasonable to expect a little sloppiness in handwritten digits. So what we've learned here is it looks like each item in the data set is a tuple containing an image in tensor format and its corresponding label. Just an aside, of course, it's a tensor because we chose to convert it to a tensor using the transform parameter when we created the data set. If we had not done that, it would actually be an image. but we want to be able to do neural network processing in PyTorch, and we'd need a tensor to do that, so it was convenient to use transform to convert it into a tensor. So let's use matplotlib to look at the first 10 images, and we will title each image with its corresponding label. So here's the code to do that. We create a figure with 2 rows of 5 images each, and like we mentioned, we title each image with its corresponding numerical label. So we run that code, and here's what we get. And you can see for the first 10 images in the data set, here's what we have: a 5, a 0, a 4, a 1, a 9, etc. So with this examination, we now have a clear understanding of how our data set is structured and what the data looks like. Much of this is explained in the data set description page, but this kind of analysis, where you actually examine the data carefully, is very useful to get a precise understanding of the data set, how it's structured, and that might not be clear from the description. Okay, so we have downloaded the data and created dataset objects. So the data is now available for use and for processing. However, we typically want to process using randomized mini batches from the data set, and we can use an object called a data loader, which makes this easy. Data loaders are iterable objects, and you'll see later that every time you iterate a data loader, it returns a randomized mini batch from the data set that can be processed through the neural network. So let's create some data loader objects from our data set. So we're going to specify a batch size of 100 items in each iteration of the data loader, and we'll go ahead and create. So here's the data loader class, where we are choosing our MNIST data set, batch size as indicated before, and shuffle true to make sure that it's randomized. So we'll go ahead and create a training data loader object and a test data loader object. And as mentioned, batch size indicates how many image label pairs in the mini batch that the data loader returns, and shuffle verifies, makes sure that the mini batches are randomized. So we're about to design and create the neural network, but before we do that, let's check for availability of a GPU. One of the advantages of PyTorch is it supports the use of a GPU, and this can greatly speed up computation. Depending on the problem, at least an order of magnitude faster processing can be achieved. Use of a GPU with PyTorch is very easy. Use the function torch.cuda.isAvailable to test for a GPU, to test if it's available and properly configured for use. And if it is available, we'll send the model and data tensors to the GPU for processing. So the following code sets a variable that we call device to either CPU or CUDA, depending on what's available. So here's the code: device equals CUDA if torch.CUDA is available, else it's CPU. And we confirm that the CUDA device, the GPU, is available. Now we're going to go ahead and create the neural network. We do this by creating a class which we have chosen to call neural net, and this is a subclass of the neural nn.module class. And here is the code for specifying our neural network. And then code for creating it. We're going to go ahead and run this code where we specify the neural net class and then create an instance of that class. And then we'll describe what's going on in this class definition afterwards. Okay, and one of the first things to note in our neural net class is there are two methods. There's a double underscore init double underscore method, and there's a forward method. And the neural network class, when we define our own neural network class definition, we must have both of those methods. We must have the double underscore init double underscore, and we must have the forward method. Both of those methods must be included in the class definition. Now let's go over each of these individually in more detail. One of the first things we do in our init method is to use the super.init command. What we're doing here is we are creating a subclass of the nn.module class, and when you create a subclass, the subclass inherits methods from the parent class. But when we write our own init method in our subclass, that overrides the init method from the parent class. But there are things in the nn.module class, in that init, in that class, that we need. And the super.init command achieves that. It essentially says, include in our init the same things that are in the parent class init. So instead of simply overriding when we define our own init, instead of simply overriding those in the parent class, this command makes sure that we continue to inherit the init from the parent class. Long story short, there are things in the parent class that we need to properly initialize our neural network class, and this command makes sure that we do so, that those things are carried down from the parent class to the subclass. The next thing we do is create a flatten object, essentially a flattening function, and describe in more detail what that is. Our data is, each image is essentially a 28 by 28 pixel two-dimensional image, but the processing will still work if we convert into a one-dimensional vector, so stacking row by row next to one another to form a 28 by 28 equals a 784 element vector. So we convert the two-dimensional image into a one-dimensional vector. The flatten function achieves this. Now there's a standard flatten function, note the lowercase f, that will flatten everything. It will turn our mini batch of 100 images with a shape of 100, 1, 28, 28 into a single vector of 78,400. Instead, if we create a function from the flatten class, note the uppercase f, this is smart enough to know to eliminate the single element dimension and merge the last two dimensions, resulting in a tensor shape of 100 elements of 784 elements. So we instead, our tensor is now 100 elements of 784 data points going into the 784 input neurons. So, a 784 element vector going into the 784 input neurons. Note, it's smart to double check and make sure that the flatten function is working. If it's not, you can include some parameters when you define your flatten function. You can include some parameters which specify which dimensions to flatten, and check the documentation for details on how to do that. The last thing we do in our init method is define our neural network structure using the sequential function. This is essentially defining the neural network layers from beginning to end, in a sequence from beginning to end. So our first layer is is called a linear layer, and that describes the connections from the 28 times 28 equals 784 input neurons connected to 512 hidden neurons. So that's what this first linear layer is the connections from the input neurons to the next hidden layer, and this is where the weights and biases are. The next layer is the nonlinear activation function, in this case the ReLU function, which is applied to the 512 neurons. The next layer is another linear layer, which is again connections from 512 neurons down to 256 neurons. After that is another nonlinear activation function, again using a ReLU function. And then finally we connect we connect from the 256 neurons down to 10 output neurons. Our nonlinear activation function, our ReLU function, stands for rectified linear unit, and it is one of many possible nonlinear activation functions which we can choose. And it is defined as the output is equal to input if the input is greater than or equal to 0. Otherwise, the output is 0 if the input is less than 0. So here's a graph of the ReLU function, the rectified linear unit. So for any input less than 0, the output is 0. For any input 0 or greater, the output is equal to the input. So that covers all the details in our init method. Now let's go over the forward method that's required for our neural network definition. Let's go over the forward method. The first thing we do is take in the input data and then flatten it using the flatten function we defined earlier. Then that data is run through the neural network that we defined up here. That data is run through the neural network, and the output from the neural network is assigned to the variable logits. And then finally, the output from the neural network is returned from the forward function. The forward function returns the output from the neural network. Something important to note is that the neural network engineer will not be using this forward function. It's strictly for PyTorch's use. PyTorch expects a forward function to be defined, so you have to define one, but the neural network engineer will not be using it in any subsequent coding. As mentioned, it's strictly for PyTorch's use. PyTorch expects it, it must be there, so you have to define it, and PyTorch will use it on its own. So that's all of the code for defining the neural network. We have the two methods, the init method, where we do a variety of things, including the defining the neural network, and we have the forward method, where we describe what happens during the forward pass of the data. Then we finally built the neural network, where we created an instance of the neural network here. And we'll go ahead and print the model as a confirmation of what we have built. And there we have a neural net object. Our model is a neural network object that does some flattening, and you can see the parameters indicating what dimensions get flattened, and then it shows the layers in the neural network that we defined, and this obviously matches what we defined before: 784 input neurons, 512 hidden, then a activation function layer, and then more connections, 512 to 256 hidden neurons, and then another nonlinear activation layer, and then the output layer, 256 neurons to 10 output neurons. Next, we will need to specify our loss function and our optimizer algorithm. Recall the loss function measures how far the model's guess is from the correct answer for each input. And adjusting the weights and biases to minimize the loss is how neural networks learn. And you can see how neural networks learn. You can see that article for details. There are multiple choices of loss functions available, and learning about these various functions is something that you'll want to do, because which loss choice is most suitable depends on the particular kind of problem that you're solving. In this particular case, where we're sorting images into multiple categories, a good choice for a loss function is something called cross-entropy loss. Cross-entropy is an idea taken from information theory, and it is a measure of how many extra bits must be sent when sending a message using a sub-optimized code. Now, if that doesn't mean anything to you, don't worry about it. That's really outside the scope of this exercise. But we can understand the cross-entropy loss if we can understand its usefulness to our situation if we examine the calculation involved in calculating cross-entropy loss. Note that each output neuron corresponds to a category, in this case a digit, a number, and the output from each neuron represents the probability that that category is correct. So what this calculation does is, for each neuron, for each output neuron, it computes the log of that neuron's output, that probability, and it multiplies times the true probability. And then it sums those products over all of the neurons and takes the negative of that to calculate the loss. Now, for a correct, for an incorrect category, the true probability is 0. For a correct category, the true probability is 1. So for all of the incorrect categories, that term in this sum is zeroed out, and only the correct category is selected. And that term is 1, the true probability, 1 times the log of the estimated probability, the output from the output neuron for that category. And this is what the log looks like, the log function looks like. Recall that from your earlier math education. And since we are looking at probabilities, since the output from the neurons are probability estimates, we're only interested in the interval from 0 to 1. So here's what the negative of the log looks like over that interval. Recall we're doing the negative of that product. So here's what the negative of the log looks like over that interval of 0 to 1. So when the output neuron gives an estimate for when the output neuron gives a low estimate for the correct category, when the output neuron gives a low probability estimate for the correct category, the loss is high. When the output neuron gives a high probability estimate for the correct category, the loss is low. Remember, we want to minimize loss. So here is the code specifying cross-entropy loss as the loss function. Loss function equals nn.cross-entropy loss. We'll go ahead and run that. So now we have specified our loss function as cross-entropy loss. By the way, strictly speaking, the output from the neurons are not probability estimates. They're proportional to probability estimates, but they're not probability estimates. However, the cross-entropy loss function does do a conversion of those outputs into probability estimates using a function called softmax. That function, that softmax function, which converts those neuron outputs into probability estimates, that's included in the cross-entropy loss function. Next, we need to choose the optimizer algorithm. The optimizer is what minimizes the loss through training and updates the weights and biases. Multiple different optimizers can be chosen, and you'll want to learn about the various optimizers that are available. All are variations on gradient descent. Excuse me. For example, some include some additional features such as extinction of the learning rate, which helps make sure that the network does not overshoot past a global minimum if it reaches it. Other variations also include including momentum, which makes sure that the network does not get stuck in a local minimum, but rather continues on to a global minimum. In our case, we're just going to choose plain old stochastic plain old stochastic gradient descent. And here's the code specifying gradient descent as the optimizer and its learning rate. So here we are, learning rate 1 e to the minus 3, and then optimizer equals torch.optim.sgd for stochastic gradient descent. Now we will specify the training and testing functions. First, the training function. Here's the code specifying the training function. We'll go ahead and run it first, and then we'll go through it to understand what we're doing in the training function. So we define a function called train neural network, and in this function we pass in, as arguments, we pass in the data loader, the model, so the neural network, the loss function, and the optimizer. All these things were defined earlier. Data loader, model, loss function, and optimizer. And then we do a for loop which loops through mini batches that are returned by the data loader. So for each mini batch returned by the data loader, we do the following steps. First, the data loader returns a tuple which consists of a tensor of images. That's what X is. and a vector of labels for those images. That's what Y is, so the actual correct answers. And we take those and move those objects to the GPU if it's available. We move it to whatever device is available. Remember earlier we set the device to CUDA, CUDA, which corresponds to the GPU when it's present. So we move these tensors and vectors to the GPU to use the GPU for processing. Next, we run the next we run the tensor data, the image data, through the neural network, and the output of the neural network goes into the variable predictions. And then those predictions go into the loss function. Both the predictions and the correct answers go into the loss function, and then the loss is calculated for the mini batch. The average loss for the mini batch is calculated. Next, we go through a number of steps which do the back propagation. So one of the first things we do is zero the gradients in the optimizer. We have to do this because PyTorch defaults to accumulating gradient calculations. So if we don't zero them initially, it will keep accumulating gradient calculations for each iteration. So again, first thing we do is zero the gradient calculations. Next, we we use the loss.backward function method to compute the gradients. This command calculates the gradients. And then finally, optimizer.step, this command actually updates the weights and biases according to these gradient calculations that were done before. So issuing these three commands does the back propagation. Zero the gradient calculations, compute the gradients with loss.backward, and then update the weights and biases according to those gradient calculations that were done in the previous command. Update the weights and biases with optimizer.step. Finally, these last few lines, for every 100th batch, for every 100th mini batch, this little section will actually print out a little bit of update information, reporting progress on the training. So it prints out every 100th batch. It prints out the average loss at that time and how many images have been processed up to that point in the training loop. Now we'll specify the testing function, and here's the code for the testing function. And again, we'll run the code first. And once it's run, we'll go ahead and go through the code in more detail. So, we define a function called test loop, and we pass in the data loader, the model, and the loss function. And we initialize a number at the beginning of the function. We initialize a number of variables. Most notably, we initialize these variables, test, loss, and correct. We initialize these variables to 0. These variables will be used to accumulate test results as we go through the testing function. Next, we do a bunch of neural network processing. Remember, the idea of the test loop is to run data through the neural network and test it and see how it performs. and that's what these code lines do. Notice that all these code lines are done within a subsection called withTorch.noGrad. And here's the reason for this subsection, this withTorch.noGrad subsection. PyTorch keeps track of, records calculations that are done during the forward pass for later use during the back propagation steps. And during the testing phase, when we're doing forward passes, there won't be any backward pass later, so there's no need to store forward pass data. And this command withTorch.noGrad turns off that calculation storing function. This saves resources and speeds up the calculating. And once we leave this subsection, this withTorch.noGrad subsection, once we leave that subsection, that calculation storing feature is turned back on. Now be aware that tensors in PyTorch default to having this calculation storing feature turned off. Specifically, when tensors are created, they would have included, they default to requires grad equals false as one of the parameters in the tensor. We are using modules from the NN library. Remember, when we defined our neural network, we defined layers nn.linear, nn.relu, and when you use those modules make sure that requires grad equals true. In other words, they make sure that the calculation storing feature is turned on. That's not normal in PyTorch. When you create tensors, they default to requires grad equals false, but because we're using these modules, this makes sure that tensors are created with requires grad equals true. And again, we use this withTorch.noGrad subsection to turn that feature off while we're doing testing. Now let's go over the neural network processing that happens within this Torch.noGrad subsection. So we use a for loop to iterate over mini batches that are returned by the data loader. And for each mini batch, we move the image tensor and the labels to the GPU. And then we run the tensor data, the image tensor data, through the neural network to generate predictions by the neural network. And then we use these two commands to accumulate results from those predictions. So first we calculate the loss using the loss function and the predictions and the correct labels. We compute the loss function. The loss function returns a tensor. It returns the average loss for that mini batch in tensor form. So if the loss were, say, 2.15, the loss function would return a tensor, a single element tensor with the value 2.15. And this .item method converts that tensor into just a number. So this loss is converted to just the number, say 2.15, and that is then accumulated in the test loss variable. And then we want to calculate the number of correct predictions by the neural network, and that's done by this command. And the way it does it is as follows. Recall that the prediction results are a tensor. It's essentially a list of outputs for each input image. So for each input image we have a vector of outputs. Recall that we are trying to sort images into numbers 0 through 9, so there are 10 output neurons, 0 through 9, and the network outputs the probability of each number, a probability of any given number being the correct number for that image. And so, for example, if the network is presented with a number 7, hand-drawn number 7, and the network correctly identifies it as a 7, it will give the highest probability to the number 7. And argmax returns which index in the vector, which index in the list of output neurons is the highest probability output. So in our example, if the network calculates correctly, index 7 should have the highest probability reported by the network, and argmax chooses that one and reports the number 7 as the chosen index. This is then compared to the correct labels, and for each label that matches the index that the neural network chooses, this comparison is true. So this statement here essentially converts the predictions to a list of numbers that are the choices by the network and compares those numbers to the labels. And for each prediction that matches the label, it returns true. So this ends up being a vector of true, false, false, true, depending on whether there is a match between the number that the network predicts and the actual correct number. Then this type torch.float method is applied to that, and that converts this this vector of true false labels to floating point numbers. So false is converted to 0, true is converted to 1. So instead of being a vector of true false labels, it's a vector of 0 and 1. A 0 for each failed prediction and a 1 for each correct prediction. Then the .sum method adds up all of those successes and failures, all 0 for the failures and 1 for the successes, giving us the total number of correct predictions by the network. And recall, this is all done within a tensor, so we have to use the .item method to convert that tensor, which has reported how many correct answers. That converts that tensor into a scalar number. So all of this essentially reports how many correct predictions the neural network made on that mini batch, and that number of correct predictions is added to the correct variable, and the number of correct answers, the number of correct predictions is accumulated as we go through the mini batches. Finally, once we've iterated over all the mini batches in the data loader and we leave this for loop and we leave this with torch no-grad subsection, once we leave that section, these last few steps calculate the average loss, and this step calculates the percentage of predictions that were correct, and then the average loss and the percentage, the percent correct is reported and printed to the screen. Now that we've defined the training and testing function, we can write a small main program that will train and test the neural network. We will go ahead and define 5 epochs. We will go through 5 epochs, and for each epoch we will train the neural network, and then once we're done training through a series of mini batches from the training data set, we will test the neural network using the test data set. And as mentioned, we'll do that for 5 epochs, and let's go ahead and run that. And we'll watch it as it proceeds. We can see here we go through epoch 1, and we can see that the loss is dropping slowly as we go through the 60,000 images. And here's epoch 2, loss continues to drop and accuracy is improving. Epoch 3, loss continues to drop. 4, 5, loss continues to drop more, and the accuracy keeps improving. And there we go for 5 epochs. As you can see, for 5 epochs, the results are not very good yet. Obviously, to get better performance, we would need to train for more epochs. This is something that the neural network engineer has to figure out, how much to train while being careful not to overfit. And that's something that the neural network engineer has to work out. So it may seem like we have gone over a lot, and in a way we have, but if you step back and look at the big picture, it turns out there really isn't an awful lot here. It may seem like a lot because we've reviewed everything in detail to make sure we convey full understanding. However, to gain some perspective, let's look at all the code without all the extra description and explanation to just get an overview of all the code. Note we're going to skip here the code that's used for reviewing the data set. We're just going to do the code that is involved in getting the data, specifying the neural network and testing it, etc. So here we go. Import the necessary libraries. Then we acquire the data. This is where we create the data set objects and download the data. Then from the data set objects we create data loaders for iterating over mini batches. Then we check for the GPU. Then we design the neural network, and then create the neural network. Then we choose the loss function and the optimizer. And then we specify the training function and the testing function. And then we run a little main program that trains and tests the network. Now, if you kept kind of mental track of how many programming lines there are really only just a few dozen lines of code. which is comparable to the size of a program that a hobbyist programmer might write. And yet we have built a world-class neural network that converts handwritten digits to numbers that a computer can work with. That's pretty amazing for just a few dozen lines of code. Of course, all of this is possible thanks to the efforts of the many engineers who wrote the many more lines of code within PyTorch. So thank you to all of you that have contributed to PyTorch. This is an example of where if we achieve great things, it's because we're standing on the shoulders of giants. Thank you. So, building, training, and testing a network is great, but ultimately we want to be able to put it to use on new data. And to support that, we need to be able to save and reload the network for later use. So we use the following code to save the weights and biases of the network to a file. And note that the common convention is to save these files with extension .pt or .pth. And here's the format, torch.save, and then the network name, the model that we were working with, .state dictionary, and then file name path, .ph. And since we named our network model, we would save it as follows: torch.save model.state dictionary, and then we'll save it in a file named modelweights.pth. So we'll go ahead and run that to save the weights and biases to a file. And then to, at a later point, reload the weights and biases, you first have to recreate an instance of the neural network, and you want to make sure that you have access to the class, the neural network definition that you originally specified. Since we've already used it, we already defined it earlier, we can go ahead and use it again. So we'll recreate the neural network and call it user model this time. And then we'll load the new instance of the neural network with the weights and biases. So user model dot load state dictionary, and then torch dot load, and then the file name modelweights.pth, and we'll go ahead and run that. All keys matched successfully. So we have recreated our original neural network architecture and loaded it with the trained model weights that we trained earlier. And we have one more thing to do with some of the modules in defining the neural network. Some of the modules perform differently when in training mode rather than when in use. So specifically, some of those modules, some of them implement something called regularization methods, which are used to resist the onset of overfitting. And these methods can include some randomness and can cause the network to give inconsistent results. So we want to get out of training mode and get into evaluation mode to avoid that. So we change our neural network to evaluation mode by doing userModel.eval. And conveniently, that command actually reports out your neural network structure, and as you can see, it matches what we previously defined earlier. So let's verify that our reloaded network works. It would be best to test with some new handwritten digits, but for the sake of convenience, we'll just test it with some of our test images. Especially since the network wasn't trained very heavily, it may be best to do that rather than trying on some brand new handwritten digits. Anyway, let's look at the first 10 images in the test data set. And this is a repeat of the previous figure generator from using matplotlib, but this time using the MNIST test data. So we're looking at the first 10 images in the MNIST test data. And there we are, 72104 14959. Now let's see if the network detects this set of images correctly. Here we define a little function that takes in the model and the image number that we want to evaluate, or excuse me, the image number that we want to evaluate, and then it assigns that image as designated by that image number to the variable test image, and then it moves that image to the GPU, and then that image is run through the model, and the results stored in logits, and then finally we use argmax to identify which index was reported the most likely identified number, and then we return that, and then we run that that function for the first 10 images, and the function returns the number that the network identifies, and then over the for loop, those image numbers that are identified are printed out to the screen. So let's go ahead and run this. And here we go, 72104, 72104, and then 14959, 17967. So it did miss a few of them. 17967. So it missed 3 of them, which is not too bad given an incompletely trained network. So, and actually the ones that failed seem plausible. This clearly a 4, but it could pass as a 7 perhaps. This could pass as a 6, and this might be able to pass as a 7 as well. So the failures are plausible and understandable, and it looks like our network where we reloaded the trained weights and biases has been successful, and it is working. We hope you have enjoyed this demonstration of building a working neural network using PyTorch, and we hope it inspires you to go and build some of your own neural networks. We wish you happy coding.